Okay, so now today we're gonna learn basically the last major thing in our toolkit for proving things, and it's going to be induction. So I'm sure a lot of people have seen the idea of induction before. Basically, you want to prove a statement for a large set, and you prove it using some nice trick, which is that you kind of imagine it as dominoes being knocked over, and then all the dominoes are knocked over as long as each domino knocks over the next one. So let's start formalizing this. So uh, the vast majority of the time when people talk about induction, even when you're past the undergrad level, I assume, you're going to be talking about proving something is true over the natural numbers. And you can do induction on all kinds of sets that have partial orders, for example. And this is a really, really powerful technique. I used it a few times before, and it's very pretty in my opinion. How you're able to generalize induction, and we're gonna see this. It's gonna be fun in my opinion. Um, but for now, we're gonna just work on natural numbers, and we're gonna learn it in the most simple case. Okay. So yeah, blah blah blah. Right. So when you want to do this, you want to show something's true for all natural numbers. You start by proving it's true for the number one. And sometimes it's going to be the number zero. Sometimes it's going to be a different number. Sometimes it's going to be a few numbers. But generally, you would probably start from proving it's true for one, and then now is the what we call inductive step. So you assume it's true for f of n for some arbitrary natural number n, and then you must conclude that it is true for n plus 1. If you do that, you get the sort of domino knocking over property, right? So you could say it must be true for any particular number because it was true for the previous number and then the one before that because they all keep implying each other forwards. Um, so yeah, dominoes is the idea. But I'm sure this idea is relatively intuitive. So now let's think about the actual template for writing such proofs. And then we'll, of course, practice the template a few times in the lecture. So first you have to pick some k. So it's a little unclear what I mean by k here. And the point is that it depends on the problem, what the value of k is going to be. And you're just going to have to think carefully about what your inductive stuff is going to look like. And the thing is that your inductive step will often, not often, it will often, yes, often need just 1, k equals 1. But there are some interesting problems where you might even need k equals 4 or something like that. And then those are nice problems. So anyway, so you pick some k and you prove that the statement is true for the first k numbers. And then now comes the actual inductive step, and it was exactly like I said before, except that you will pick n being at least k, and then you assume f of n and prove f of n plus 1. So the point here is that you knock over these dominoes by hand, the first k, and then the inductive step knocks over the rest of them for you. Okay. Okay. So yeah, that's pretty much all the standard proof techniques. Pretty much any proof you're ever gonna read is gonna look more or less like something I've shown you before, although it may be slightly more complicated. Um, but yeah. Okay. So let's actually do some induction. So this is a very trivial problem, but it's obviously very good to start with this kind of thing. So prove that for any natural n, there is a set, so a subset of natural numbers who has the cardinality of n. So you don't need induction, obviously, right? You can just pick s is the first n natural numbers, but we don't want to do that. We want to do it by induction, just to teach you guys. So in this case, this is a regular induction problem. We pick k equals 1. Again, I only know this by actually thinking about the inductive step, but in this case, the proof just works for k equals 1. So we assume f of 1 is true. Sorry, we don't assume. We show it's true directly. And we show it's true by just showing you how to do it. And so this is a subset of the natural numbers, and its cardinality is 1, so f of 1 is true. Okay? Okay, so now we have to do the inductive steps. Now if we look at our template, so we have to universally instantiate some n that's at least k. So we instantiate n, which is at least 1. We don't know anything more about this number n. and we assume f of n is true. And so a lot of induction proofs basically write themselves because when you assume f of n is true, you get some statement. And in a lot of induction problems, this will look like just some equation. So you get to assume that equation is true. And what I mean by the proof writes itself is that you have this equation, it has to work out to equal this other equation. This other equation comes from, of course, f of n plus 1. And so you just need to fill in the dots between these two equations. So as long as what you're trying to prove inductively can be done like that, it tends to write itself. So okay, so in this case, it's not as clear because we don't have an actual equation, but we do have f of n is true, and this is actually quite nice. So we have a set, I should have written subset of natural numbers here, but it has size n. And now f of n plus 1 is that we need to have a set which has n plus 1 elements. So I need to add one element, but I need to be a little careful because I can't, for example, just add the element n plus 1, right? If I add the element n plus 1 to the set, it might actually stay the same size if that element is already in there, right? Because sets don't have duplicates. So to avoid having a duplicate, what I do is I take advantage of my the property we discussed last time while discussing homework 2. And I know that oh, actually, this comes from a different property. So let me rephrase this differently. This just comes from the fact that we can take a maximum over a finite number of numbers. So we have m being the maximum inside of S, and we just put 1 plus that. And then that's definitely not a duplicate. So now I've increased the size of my set by 1, and so that means I have the right size subset of naturals, and okay. So I feel like this is pretty straightforward. It's nice to start with sort of trivial statements to see the template in action. And so let me just be really redundant here. Let me just go through the template and what happened. I picked k equals 1. I proved it for k equals 1. And then I instantiated something which was at least k. And then I showed that f of n plus 1 follows by assuming f of n. That is how every induction proof ever is going to look, basically. All right. Let's talk about a more fun statement. I'm sure you guys have seen this. Okay, for all natural numbers, the sum of the first n natural numbers is this nice expression. So this is the number of pairs you can choose if you have n elements. Sorry, subsets of size 2 with n elements. Or maybe this is n minus 1. Sorry, I might have that the wrong way. I always get the off by 1 wrong. But yeah, anyways. So this is the kind of example where I mean that it tends to write itself. So first we start off by just formally writing what f of n is. It helps sometimes to make it very clear what f of n is in sort of a truth value. So it's just equality here. So we pick k equals 1. This is very clearly true. You just plug in 1 on both sides and it's fine. And then we do our inductive step. So we instantiate something which is at least 1, at least k. We assume f of n, and like I was mentioning before, assuming f of n, right, gives us this equation. Okay. So now we have this equation, and I want to conclude f of n plus 1. So I have a different equation that I want to show is true, and it's just incrementing this by 1 and incrementing this and this by 1, right? So here's a kind of nice way of writing this. So I have this, right? So this is the sum of the first n plus 1 numbers. And I want to show it's equal to this over here, right? I've just substituted n for n plus 1. So, okay, I say the sum of the first n plus 1 integers is the same as n plus 1 plus the sum of the first n integers, right? So I just pulled off the last term. And then I said, okay, well, I know what this is equal to. The sum of the first n integers by f of n is equal to this. And then I do some algebra off screen, and then I conclude with this. So I'm done. Okay. So I think I guess a more natural way to do it would be to write this is equal to this as an equation, and then manipulate both sides at the same time by adding n plus 1 on both sides. But I wanted to do it nice, one-liner, and this is how you can do it that way. Okay, any questions on how this is working? Good. Okay, so while you're Okay, I'm seeing an advertisement for DoorDash. That's quite good. I'm a little bit hungry. Um, while you're looking at these proofs, right, in the lecture notes, uh, do keep in mind that this kind of style, I tried to write every single proof in here as well as I could. So I want these to really serve as, I guess, data points for you to learn from how to write proofs. So I really examined every sentence, and I said, is this sentence necessary? I examined the sentence order and the length, uh, and basically tried to optimize this. So when you're writing your proofs, it's a really good idea to go back to the lecture notes and see how these were done, how these were written exactly, and try to emulate those. So I do think that will improve the quality of your proofs in general. Okay, so now we have like a real math thing. So I don't know if many people would have seen this before, but basically, okay, we're talking about GCD, and uh, hang on, what's going on here? Have I talked about divisibility yet in this class? I don't think so. Um, that's not good. How'd that happen? Did I skip it? No way, I skipped it. Um, that's not good. Not in here. Oh, I think I know. Okay, it was in the homework. Okay, good. Okay, it's like did I just completely miss it? Okay, so we went over this in the homework, but I think not everyone who's in the lecture actually does all the homework. So I will just review the definition of divisibility real quick. Oh, I really thought I was losing it. Okay, so it's a very simple definition. So if x divides y, then there is some integer k such that y is equal to k times x. So for example, if 3 were to divide 9, then there's the integer 3, which makes it such that 9 is equal to 3 times 3. So very straightforward definition. Um, hopefully that makes sense. Okay, so the greatest common divisor, and I guess I haven't really defined it, but okay, I'll define it right now. It is the maximum element uh, in the intersection of divisors of A and B. Right, so take the set of elements that divide A, take the set of elements that divide B, intersect them, and take the maximum. And the intersection ensures that you only have divisors of both A and B. Okay? All right, so now we've formalized the definition of GCD, very good. And now we can actually talk about the statement. So yeah, if you just do this weird tricky little thing, if you swing B around here and take the negative of A, then it turns out that GCD remains the same. And this is actually a very important property in the Euclidean algorithm, which actually we're gonna use this property straight up very soon. Okay, cool. So yeah, so now in order to actually do this, we have to prove this statement first. So a number is a divisor of A and B if and only if it is a divisor of B minus A and B. So the point of saying this statement basically is that we want that the intersection of divisors of A and B is the same as the intersection of divisors of these two numbers. Because if those two intersections are the same, then obviously the maxes are the same. If the maxes are the same, then the GCDs are the same. Okay, so all we really need to do is prove this. Okay, so this is a bit of an irritating statement, at least in my opinion. So again, we have an if and only if. So like I just mentioned, while we were reviewing the homework earlier, we have to do two directions. So let's do the forward direction first. That's most natural. So we have to assume this and conclude this. Okay. So, and by the way, this doesn't use induction. The proof we're going to do below is going to use this in induction. Okay. So suppose that G is a divisor of A and B, And just to make it crystal clear why we're doing that, we're talking about a set, right? We're talking about a set of divisors, the intersection of the two sets of divisors. So we're talking about a subset in the forward direction. Okay, so to prove subset, we're doing the universal instantiation like you're used to, blah, blah, blah. So we're picking G, so it has to be divisor of A and B. And now we need to show it's both a divisor of this and this. So because it's a divisor of A and because it's a divisor of B, we have these integers. This comes from the definition of divisibility, right? If G divides A, then there's some K such that GK equals A. So we have this. And we also have GK prime equals B. So this is just from definition. And now we do a neat little trick. We combine these equations. So we just subtract this equation from this one. We use an algebra. And then we find that G times this guy is equal to B minus A. Okay. So that means G divides B minus A. And if there's any tip for having found this trick, it's that I need to show G times something is equal to B minus A. And I only have these two original equations to start with. So like the induction stuff I was saying before, when you assume an equality and you have to conclude an equality, it kind of writes itself sometimes. Okay. And we also have to conclude that G is a divisor of B, but that's our assumption right here, right? So that's fine. Okay, now the reverse direction, and it pretty much works out the same exact way. You do the same thing with K and K prime, and then you you subtract one equation from the other again, and you find that G must divide A, and B was on both sides, so we're done. Okay, so now we have this very irritating statement out of the way, and now we just formally write the logic I was saying before about intersections of sets, and now they're the same sets, so then they have the same maxes, and therefore they have the same GCD. Okay, so this property is used for Euclidean division. Sorry, Euclidean division? Yeah, you can call it that, Euclidean algorithm, whatever. But we're going to use it for something with the Fibonacci sequence, this is actually a really fun fact. Okay. So, but any questions about this divisibility stuff? So it's no coincidence that I'm talking about GCD and divisibility here. These ideas are going to show up again in different places. Okay, we have two head scratches, so I'm going to assume everything is okay. All right. So we have the Fibonacci sequence. We're going to now formally define it for everyone. Hurrah! So f1 is 0, f2 is 1, fn is the sum of the previous two ones. Surprise! This is actually not a surprise. But okay, here's the fun statement: f of n and f of n plus 1 are coprime for any n, and I think that's really neat. So just reminding you, two numbers are coprime when their GCD is 1. Okay. So basically, numbers should only divide two consecutive Fibonacci numbers if they are 1 or minus 1. But sometimes when we talk about divisors, we implicitly rule out negative numbers which divide them. Okay. So anyways, we're going to do this with an induction. And so now let's do our template again. Again, stage 0, if it helps you, and I think definitely at this stage you might want to do this at least in your Scratch work, just to find some proposition that you're trying to prove inductively, because you won't, necessarily know as easily what it is that you want inductively. Maybe there's stuff before that's not going to be done by induction, or stuff afterwards. So of course we want the statement that the nth pair of consecutive Fibonacci numbers is coprime. So now we pick k equals 1. It's very typical to pick k equals 1. So we just prove it. The GCD of 0 and 1, the first two Fibonacci numbers, is 1. And I didn't show why it's 1, but I hope you agree with me that it's 1. And now we do the actual fun part, which is that we will do the inductive step. So assume f of n is true. So we get to assume this. That's great. And now what do we want to prove? Well, we want to prove the same statement is true, but for f of n plus 1 and f of n plus 2. So we have this. And then f of n plus 2, by definition, is the sum of the previous two Fibonacci numbers. And then very slickly, I've just used this property from before. That you can take the second number you can subtract out the first number and then replace the first number with that value. So I took this number and I subtracted out this number and I replaced that number with it. And then I flipped the numbers around because, of course, it's symmetric. And this has GCD1 because f of n is true. Okay, so very, very clean proof, but a little bit of machinery going on, and I think it's a very interesting result. And you might be tempted to actually go look at the Fibonacci sequence and see like, oh yeah, every consecutive pair is actually coprime, and it's pretty interesting. Okay, so that actually basically concludes induction. You're gonna have some more induction problems in the homework. Okay, by some I mean that you're gonna have 5. They're fun problems though. So do enjoy. And oh, this is a very fun problem. So I would really recommend doing 6, especially if you're a computer science student. Being able to do induction on complex objects is very good. But don't stress yourself out too much with this problem. And this was again a problem introduced by the previous year's instructor, and I don't really like these kinds of problems. But if you like playing with big computations, doing algebra, then go ahead. It will only help you to do it. I think these are not as bad in my opinion in terms of like the ratio between effort and learning as the extra problems from the last homework. Yes, this is Adam Swords. Think I no, I don't think I made this sword, or maybe I did. Yeah, I think I made this up. But it's fun. Anyways, bonus points for determining big O. Um, well, actually, the implementation of this algorithm isn't really well defined. So if there exists j less than k, um, so you could do this really poorly, and you can write an N4 version. But I imagine you can do so. This is going to run n squared times, at most. Um, I don't know if you can necessarily check this very quickly. Maybe in log time. Okay, I will give you some bonus points if you write an n squared log n implementation of this algorithm. So have fun with that. I think possibly even an n cubed might be a little tricky, but yeah. Anyways, so we of course have more to this lecture. This is I guess the second half. It's a different topic: humility and why we're always wrong. So the counterpart to how to always be right. This is just gonna be a bunch of fake proofs. I think it's really instructive to see common errors in proofs, and we have the source here, so you can go here if you want maybe a little bit more discussion. What kind of leak code ripoff? Oh, there's a lint code link here. So I think lint code. Let me throw this up here. Lint code is you have a linter in the editor, and I think all the solutions are like free or something. It's literally all the material on LeetCode. It's like some Chinese website. Anyways. Um, okay. Where was I? Here. Okay. So I did no prep for this lecture, so I don't remember anything here. Okay. Let a, b, and c be integers. If a divides bc, then either a divides b or a divides c. So actually, can someone tell me, is this statement true? Is this statement true? I picked 3 integers. Okay, just for simplicity, you can have them be natural numbers. If a divides bc, then a divides b or a divides c. I had like a half nod from one person, and then I had a shake of the head from the same person, and then a confused expression. Okay. So this is not it's not a coincidence that the statement is here like this. This is a statement that you're going to explore later on in abstract algebra, and you will talk about different structures of numbers. But basically, This statement is false, and it's important that it's false. I'll tell you that. Can anyone give me the counterexample, knowing that it's false? Which line? Sorry, I'm confused what your question is. I said, can anyone give me a counterexample? Let me know if anything is still unclear. Okay, so we have a equals 6, b equals 3, c equals 2. So let's check. Yeah, so b times c is 6. I agree. 6 divides 6, but 6 does not divide 3 or 2. Good. You can actually give a kind of more instructive counterexample, and that comes from the fact that basically, think about the prime numbers here, right? So basically, let's say A is the product of two primes, and one of the primes is only in B, and one of the primes is only in C. So then neither this nor this is true, because B and C are both missing one of the primes that's required to be in it to have A be a divisor. Oh wait, sorry. I've done this completely the wrong way. Oh wow, I'm thinking about a different statement. Okay, sorry. Yeah, ignore me. Uh, why did I think that? Oh, because the statement from algebra is the other way around. Sorry, yeah, I was completely confused. Normally you have BC here and then A here, and then that's a lot more instructive. Okay, so yeah, why we're always wrong? Maybe I should be a little bit more helpful. Okay. Yeah. Anyway, so the wrong proof here is something silly. It's something I mentioned a few times before. You instantiate exact values for these variables, and yeah, and then obviously it works for these specific values, but it doesn't work in general. And this is still very common. So, okay, so someone in chat actually mentioned something that looks like this. I think it was exactly this. Um, but yeah, so we have something known as Euclidean division. So you can calculate this using the nice GC formula from before. But anyways, so Euclidean domain. So I want it to be fancy. Um, so Euclidean domain, you can just for now assume that Z is a Euclidean domain, and whenever you have A is some integer and B is non-zero, then you have unique Q and R such that this is true, and R is between zero. Sorry, R is at least 0 and less than absolute value of B. So that was a mouthful. So the way to understand this is that let's say you're dividing A by Q, just like as a quotient, right? Then Q is like the whole number result that you would get, and R is the remainder. So Q, I would kind of say, stands for quotient. So for example, if I had A equals 5 and B equals 3, then I think of, okay, let me quite literally show this. A equals 5 equals 3. And that kind of shows you why B can't be 0, because B is like the denominator here. So when I do 5 over 3, if I wrote this as like a mixed fraction, right, out of 1 plus 2 over 3. And so the whole number part is this. So that would be my Q. So I had 1 times B plus, and then my remainder is the 2, right? Plus 2. And then you can see I plug in 5, and I plug in 3, and then the equation works out. Okay, so that is Euclidean division. And you can always do this in Euclidean domain. And I've written for you here that integers are Euclidean domain. Okay. Right. So Q is close to the quotient A over B. So it's I guess formally it's the floor, and then R is whatever's left over. Okay. And I have a different example here. Okay. Okay, another definition here. So A mod B, computer scientists are very familiar with this. It is just the value of R if you use A and B as above. right? So 7 mod 2 is 1, 7 mod 3 is 2, blah, blah, blah. Okay. Let A and B be integers, where A is 1 mod 3, B is 2 mod B. Okay, this is a fun problem. So it's just showing an example of how modular arithmetic kind of works out the same as regular arithmetic. So I kind of added 1 plus 2, and I did mod 3, and I got this. And it was the same as adding A and B, and then just modding by 3. Okay. Um, here's the fake proof. So again, I haven't tried this in a while, so let's see what's going on here. So instantiating A and B looks good to me. Such that this is true and this is true. That looks fine to me because that is how we start up the proof. Then it follows by, actually, let's hide the results. Hopefully no one's read it yet. Um, then it follows by the division algorithm that there must exist some Q, such that this is true, and I agree because B is not 0, and A and B are elements of a Euclidean domain. Okay, B is equal to 2 mod 3. So you can also write, there's a typo here. So right, so now we've written this using Euclidean division and blah 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 blah. We did some algebra. You can assume that algebra is correct, and then we find that A plus B equals 0 mod 3. So I actually skimmed over the error. I did spot it as we were writing this. So this algebra is correct. I'll tell you that. And so the result of this algebra is that A plus B is equal to this. So the division algorithm tells us that, okay, we wrote this number as some value times what we're dividing by. So and then the plus r is missing, right? So the r equals 0 basically. So that means that A plus B is 0 mod 3. So this part is definitely correct. So does anyone see the error exactly here? And it's very subtle. Very subtle. Okay, I have a yes, but a refusal to elaborate, it seems like. Okay, just hit the raise hand button if you think you spot the error. One. Paul is no longer claiming that he's spotting the error. Okay, Paul has been writing out the answer. Good. Um, so, let me share this. Let me share this. So, this is, I guess, a little bit vague what is exactly wrong here. But, yeah, the point is that, I've reused the variable q, and you can't do that. And this is actually a mistake I've seen many times while grading uh, computer science discrete structures 1 proofs. So yeah, you can't reuse q. So here I would just have to use q prime, and it's quite similar to how above I used k and k prime because the context is just different, right? So you have to be careful. Where were we? Yeah. So fun story. So I was in 351, which is the Intro Abstract Algebra 1 course, and we were doing like some problem solving session, and we were in groups, and I decide to work on I guess a tricky problem, and I spent some time. I come up with a solution, and I had actually done this, and it had made the problem quite trivial. And everyone in my group looked at it and they said, "Yeah, this proof makes sense." I was like, "Oh, okay, then it's probably right." And then I took a closer look and I was like, "This is completely wrong." And yeah, so yeah, just be careful. Always, when you're introducing a variable, make sure that you're not accidentally using a variable name that you used before, because then you might accidentally group them together in bad ways. And this still works, of course. What happens is you end up getting q plus q prime here, and then the proof is correct. So the proof kind of works out almost the exact same way, but it is technically not a correct proof. Okay. Um, so now, very fun concept from graph theory. So Daikon radius number. So we're not really okay. I'll read the definition for you. So Dicon range number of an integer x is a number that describes the number of graphs of isomorphism class x to the p, where p is the smallest prime larger than x. So this is convoluted definition. Involves prime numbers, graphs, and this weird exponent, and isomorphisms. And we're not going to get into the details, but it is a fun thing to talk about. So we write it as dr of x. And the only really important thing here is that it's a function that is going to take in a single integer. Okay. So let's talk about this. Every set of integers of size n all has the same dr number. Okay, so this, you can just assume that this is basically a false statement, because why would it be true that the dr number for every single integer is the same? That probably doesn't make a lot of sense. Okay, so here's my fake proof. Okay, so hopefully no one spoiled themselves. Okay, so stage 0, let's write the proposition. So yeah, we have to be careful here. When I say every set of integers of size n has the same dr number, I need to formalize this. So I'm talking about every set of integers of size n. So I have to say for every subset of the integers, if it has size n. Okay. Now I have to show that they have all the same dr number. So every pair of elements in the set has the same dr number. So this is a little tricky to write. But there are other ways to write it. For example, I could take the set of dr of x for x in S and say that this has to have cardinality 1. That's another way of doing it. It's a little weirder to do that because you're kind of abusing the fact that sets don't have duplicates. But anyways, I think this is probably the most elegant way to write our statement here. So f(1) we have to talk about. So obviously if there's only one integer in the set, right? There's only one dr number in the set, so every number in the original set has the same dr number. That's trivial. So now let's suppose that f of n is true. Okay. So again, this kind of thing, we want to always use as much as we can what we have from f of n. So we have this set of size n, and everything in here has the same dr number, right? We have this. So this is a very strong statement, right? So now we want to make it true that okay, yeah, sorry. Sorry, I phrased that wrong. I said that we have a set. That's not true. We don't have a set yet. We have the property that any set of size n has this conclusion. So now we arbitrarily instantiate a set of size n plus 1. So yeah, we have to be really careful here, and I'm sorry I'm sloppy. So now we instantiate something, because now we're trying to prove f of n plus 1, and in f of n plus 1, we have to start from this assumption, right? We have a subset of integers, and the size is going to be n plus 1 for f of n plus 1. Okay, so we can order the elements. You can always assume that you can order elements in a finite set like this. So what we do now is we split this apart into two sets. It's not going to be partition. It's just two different sets. So S1 is going to be the first n elements, and S2 is going to be the last n elements. Okay. So now both of these sets independently, S1 and S2, have cardinality n, right? Because all of them, for both of them rather, I took out one element, either the last element or the first element. And f of n is true now. So that means that all of these guys have the same Dicon radius number. All of these guys have the same Dicon radius number. But that means that all the values between A2 and AN have the same Dicon radius number. So we could just call that x. But since A1 must have the same Dicon radius number as, for example, AN, then A1 also has a Dicon radius number x. And same for AN plus 1 and AN, for example. So that means that all numbers inside of S have the same Dicon radius number x. So basically what I did was I split it apart into two smaller sets. And I noticed that they kind of just make sure that everything has the same Dicon radius number. Okay, so everything inside this S with n plus 1 elements has the same Dicon radius number, so f of n plus 1 is true. So what is the issue with this proof? So I did not spell radish wrong. This is radish, a mathematician. Okay, we have some thoughts. Dicon radish. Look, just focus on the proof. Focus on the proof. I can see that Paul is tapping around because his entire room like flashes different colors. Okay, so we have people searching up Dicon radius, even though we've literally only used the fact that it's just a function. Uh, so I'm sensing that maybe there's a little bit of difficulty focusing on the like maybe four sentences in front of them. Okay, my call ends in 10 minutes, guys. No more radish talk. Max has typed up a lot of numbers. Um, if you look at it very carefully, you will actually see what's wrong. So if you so I spoke differently, by the way, from what's actually written in the proof here, and the proof is written very concisely with the intention that you should probably try to pick every single line and really beat it up. See, is this 100% true? I will start narrowing it down a little bit. This is definitely true. No doubt about that. This is obviously fine. This is how you start induction. Uh, I'm assuming so, Rohan. Um, this is true based on the inductive hypothesis. This is just a constructive step. This is also a constructive step. So somewhere in, say, somewhere in here, because this is just conclusion. This is also definitely true. So when I wrote my induction, right, I actually skipped a very small part of my template. Can anyone tell me what in my template I skipped? Actually, take a quick look. So we did this. I skipped something in here. What did I skip? No, I had up event. I had up event. Yeah, we started from event. Um, and we tried to do this. So what did I skip? I skipped this. And I skipped this to mislead you a little bit. So what was K? K was 1. Okay. Go carefully. So now keeping that in mind, I skipped writing n is greater than or equal to 1. Where does that put your attention? Yes, it is suspicious, Max. The size of S1 is always going to be n because I'm just putting the first n elements. That's fine. I'll give you guys one more moment. If you have any guess, just try and throw it up. Okay, the wrong statement is this. That is the wrong statement. So, or sorry, that is not the wrong statement. I'm having a stroke. Um, wait, let me read it carefully. Oh, I actually didn't precisely write the wrong statement. It's this. It's this. It's this. Yeah. So I used misdirection. I used misdirection. Sorry. I thought I had written it S1 here. That's why I got it wrong. So the problem is that A2 is not necessarily in S1. Okay. So how could A2 be not in S1? What is basically the only way for that to happen? Yeah. If n equals 1, basically. Yeah. Sorry, I got that wrong. Yeah, so if n equals 1, right? And that's what I was trying to show you with the n greater than or equal to 1. So if n is 1 exactly, right, then s1 is a1 and s2 is a2. So yes, this is true, of course, and this is true, and this is true, and this is true. All of this is fine, but then I use misdirection because this doesn't follow. A2 is just not in S1. So yeah, so this doesn't follow, and then this obviously doesn't follow, and then this whole statement is just complete nonsense, right? Okay, so the inductive step doesn't work at the very beginning, so you never start knocking over all of your dominoes. If you did actually prove f of two, right? If you were able to somehow do f of two, then that would do everything. And by the way, so just examine it. F of two would say that any pair of numbers have the same Dicon radius number. And of course, if any pair have the same, then all of them have the same Dicon radius number, right? You don't even really need induction for that, right? Okay. So um so this is a problem that I just kind of stole from all horses are the same color. I don't know if anyone has seen that before. Like you do the same exact thing, but instead of mapping integers to integers, you map horses to their colors. Um, and yeah, so you just do the same trickery, right? You line up the horses, and the first end have the same color, the last end have the same color, and so the middle one must be the same color as both ends, and then you're done, right? Okay. And I have another revelation, which was already spoiled slightly. Yeah, Daikon radius is not a real thing. Um, so if you yeah,
大根、
yeah, good catch. So I don't think Daikon radish is that a phrase by itself? Can I play it again? Absolutely.
大根、
It goes slower the second time. Hopefully that was clear enough for you. Um, yeah, Daikon radish isn't like a phrase. It's just translated. Anyways, I really do enjoy doing that. Okay. Um. I think the meeting is over soon. In under a minute. Oh no. Okay, we're gonna hop over to a new call really quick. Uh. Okay, I sent the message and I'll put it in Discord too. I'll see you in a moment. Hello everyone. Okay. Oh, I have to share my screen. Okay. All right. A couple more wrong proofs, but they're nowhere near as interesting in my opinion. So this is a theorem from Fermat. This is added by the previous year's instructor. I think this one is a pretty interesting thing. So, okay, let f be mapping an open interval on the real numbers to the real numbers, and let it be differentiable on this interval. So we never talked about differentiability in this course. It has a very rigorous definition, but let's just ignore that for now. If f attains either a local extremal value at some c inside of the open region, uh, sorry, either. Why does it say this? Okay, the word either shouldn't be here. If f attains a local extremal value at some c in the open interval, then the derivative there is 0. Um, so get rid of error. So let, for example, oh, so this is just an example of the statement. So if we're mapping the open interval -2 to 2 to the real numbers using this parabola, then we have a local extremum at x equals 1, and if you take the derivative there, then obviously you get 0. Okay. Um, huh? Wait, what? Okay, so we're using a specific function as an example, and then doing a proof with that function. So I guess it would be wrong for that reason. Um, I don't know what happened when he actually did this lecture last year. I guess we might have had a note to fix this to not do that. Okay, I'm gonna ignore this. Sorry. Um, okay, yeah. Here's a note on converses. I think what's happening, yeah, what's happening here is that uh, we're talking about the converse, but just for the example. Okay, anyway. Um, so yeah, so P implies Q is an implication. Its converse is Q implies P. You've probably seen this in geometry or something. Um, okay, so something that is commonly done wrong in English is that a statement and its converse are not logically equivalent. So we were talking about this in like VC the other day. Um, so I think the example was if you pass the test, then you pass the course. Um, but the converse would be if you pass the course, then you pass the test. But that doesn't necessarily have to be true because, for example, let's say if you pass the course, which means you get at least a 70%, um, then you will definitely get a passing grade in the course. But maybe you only need a 50% on the exam to get a passing grade in the course. So if you pass the course, you may fail the exam still, or you might not. It's not clear. So the converse is not logically equivalent to the actual implication. All right, that is the end of the lecture. I'm very sorry for this sloppiness. I don't understand what was going on in this. And I also oh, hang on. Oh, I see what was going on here. This is we're not doing a proof of this at all. We're gonna use this theorem to prove this. Okay, okay. Let's. I'm so sorry. Okay, let's try that again. So let this be an example function, and we want to show that f attains the local extreme at x equals 1. Okay. Um. So I mean, we know logically, right, that it attains the local extremum there. But let's look at how this proof does it, right? So we're trying to use Fermat's theorem here, which is that if the function is differentiable in an open interval, and it attains the local extremal value at some point, then the derivative there is 0. Okay, and here we say that because when we differentiate at 0, when we differentiate at 1, we get 0, then this is attaining a local extremum there. Okay. And the point is that you can't use Fermat's theorem like that because it's literally just the wrong direction. That's what's going on. Sorry, I totally botched that example. Okay. Yeah, so sorry about the sloppiness here. And again, when saying that this is wrong, and also when messing up my counterexample for the divisibility one somewhere around here. Okay, any questions on the contents of this lecture? No? Okay, thank you. And next time I will. Okay, we do have some questions. Prove that Paul's name is spelled with 4 characters. I don't want to have to formalize the definition of like uh a free group on letters. It's too irritating. Favorite vegetable? Uh, it's a good question. I usually don't eat vegetables, so it's actually a hard question. Maybe mushrooms. I think mushrooms. Different types of inductions that will be taught later on. Yes. Um, I'm going to show you some very fun induction. You should be very excited for it. Um, that's not sarcastic. It's genuinely a very fun thing. We have a lot of Shut Up Nick, Shut Up Paul. I love daikon radish, and naan bread. That's not a vegetable, but that's okay. Naan is also a type of bread, so that's like saying bread. Anyways, All right, thanks everyone for coming. I'll prepare better next time. See ya.